Welcome to This Explainer. Today we're plugging straight into a wild, neon-drenched combinatorial universe of nonlinear optics. You can think of This Explainer kind of like an 80s arcade map, where we're going to explore the absolute limits of how we manipulate light. We're going to explore this physics front to back, looking at exactly how we split photons to create infinite possibilities. And then we're going to flip it back to front, revealing the totally mind-bending reality of what happens when we force those exact same photons to recombine.
Okay, let's dive right into this with the absolute bedrock of our quantum universe. The entire field of nonlinear optics pretty much boils down to this single, elegant quote. A pump photon splits or combines if you conserve energy and momentum. That's literally it. Whether you're building a completely unhackable quantum computer or a next-generation sensor, you're really just playing an intricate game of balancing these two sides of the cosmic ledger. Here is our roadmap for today. First, the golden quantum rule. Second, enter the crystal zoo. Third, brute forcing infinite possibilities. Fourth, the self-zeno photon trap. And finally, future quantum architectures. Part 1, the golden quantum rule, splitting and combining. To set up the baseline physics of how we bend light to our will, we have to look at this golden rule. To split a photon, the energy of your incoming laser pump must perfectly equal the energy of the two new photons, which we call the signal and the idler. Now that is non-negotiable. But the momentum conservation, well, that's where the magic actually happens. We need the change in momentum, also known as delta K, to be exactly zero. And the crucial point here is that we can force this to zero using 4 specific tuning knobs: the crystal's angle, its temperature, the laser wavelength, and the crystal's polling period. If you master these 4 knobs, you unlock infinite combinatorial possibilities. Moving on to part 2. Enter the crystal zoo. Select your player. With the rules established, it's time for character selection. We've got about 60 mainstream crystals divided up into distinct chemical families, and each one has a totally unique superpower. Borates, like BBO, those are your high-damage ultraviolet workhorses. Then you have the KTP family, which absolutely dominates the telecom spectrum. Then there's the mid-IR chalcogenides, like ZGP, operating in the 1 to 18 micron range, where people rarely even look. And finally, the wildcards, the organic supercrystals. Rapidly comparing these players lets us see exactly which chemical family we need to manipulate entirely different spectrums of light. Now within the zoo, we have our heavy hitter, PPLN, or periodically poled lithium niobate. People often call this the silicon of nonlinear optics. By artificially flipping the crystal's domains, a neat process called quasi-phase matching, we essentially inject artificial momentum right into that golden rule we were just talking about. This brute forces the physics, giving PPLN a massive nonlinear coefficient of over 15 picometers per volt. Honestly, it is incredibly bright. But just look at the sheer scale of the organics, like DST and DSTMS. These are ionic salts that boast a nonlinearity 10 to 50 times larger than standard inorganic crystals like lithium niobate. Under conditions where standard crystals produce absolutely nothing, these organic powerhouses are busy generating ultra-strong terahertz fields. It's kind of like finding a secret, overpowered weapon hidden deep in the code. Part 3, brute forcing infinite possibilities, the cheat codes. So, having selected our crystals, let's pivot to the exact engineering manual for generating whatever quantum state you want. Basically, your laser is your power-up. But it's not just about picking a color from deep UV to mid-IR. The temporal structure of the laser physically alters the entanglement properties of the photons. If you use a continuous wave narrowband laser, you get perfectly indistinguishable photon pairs. But blast it with a femtosecond broadband pulse, you suddenly generate a broad, time-energy entangled spectrum. Changing the time structure literally changes the reality of the photon itself. How wild is that? And this brilliantly illustrates exactly how engineers map the search space. It's a really simple 4-step cheat code. Step 1, pick your crystal's transparency window. Step 2, solve the Sellmeier equation to find the refractive index, which is essentially figuring out how light bends in that specific material. Step 3, choose your polling period to perfectly balance the momentum. And step 4, decide what quantum property you actually want to extract, like polarization or frequency entanglement. It is a completely deterministic recipe for creating pure entangled light. All right, part 4, the self-zeno photon trap, back to front. Brace yourselves, because here is the plot twist. We've spent the first 3 levels going front to back, right? Splitting photons apart. Let's flip the script. What happens if we go back to front? What if we take those beautifully split photons, try to combine them, and then trap them inside a crystal? And more fundamentally, what actually counts as a measurement in quantum mechanics? Does a scientist in a lab coat physically need to be looking at it? To answer that, we have to de-jargonize something called the quantum zeno effect. In a normal zeno effect, an external observer measures the system so frequently, say like every nanosecond, that the quantum state literally freezes and cannot evolve. But in a self-zeno setup, we remove the scientist entirely. We engineer the crystal so brilliantly that its own internal nonlinear physics acts as the observer. The system continuously measures itself. So how do we actually fool a photon into measuring and trapping itself? We use the master playbook, the 4 tricks. The blockade trick forbids pairs. The mirror trick shifts the cavity resonance. The suicide trick uses an absorber. And the interaction-free trick uses a polarization loop. Let's take a closer look at 2 of these really cool rule-making mechanics.
Notice how the blockade trick exploits the mere threat of detection. Imagine a 1550 nanometer photon just resting inside a PPLN cavity. A second photon tries to enter. If it did, their combined energy would perfectly phase match to create a 775 nanometer photon, which would immediately leak right out of a mirror and be lost. Nature hates this, right? It abhors this detectable loss, so it creates a zeno blockade. The mere possibility of that 775 nanometer leak traps the first photon safely inside, completely refusing the second one entry. Then we have the bizarre reality of trick 3, the suicide. Here, you use a material like our organic friend DAST, which is perfectly transparent to one single photon, but instantly absorbs 2. Nature hates this dissipative loss so intensely that the quantum field effectively learns to never put 2 photons in the same place. Its zeno suppresses double occupancy before it even happens. The crystal's atoms did the measuring, not us. Finally, part 5, future quantum architectures, the final boss.
This is where this back-to-front physics unlocks literal never-before-seen tabletop technologies. The biggest breakthrough is self-zeno-trapped swapping. Standard entanglement swapping is messy. It fails half the time. But this self-zeno version, it continuously measures itself. It forces the system to only live in the successful entangled subspace. If a failure mode tries to occur, the zeno rule just dumps it as loss instantly. It requires 0 external detectors to herald success. It just works automatically.
Think about what this actually unlocks for us. We finally get a deterministic quantum repeater that completely beats that old 50% success limit for long-distance secure networks. We get deterministic fusion, which solves the biggest bottleneck in building massive photonic cluster states for quantum computing. We even get hybrid architectures where PPLN waveguides can trap photons directly into long-lived Rydberg atom matter memories. And taking this into the real world, just look at mid-IR ghost swapping, for example. By using the zeno effect, we can entangle a visible telecom photon with a mid-infrared photon. The telecom photon stays safely in our easy-to-read zeno cavity, while the mid-IR photon goes off to sense specific chemical signatures. We can sense chemicals using cheap telecom detectors simply because the entanglement is preserved by the zeno rule. It's a brilliant hack. Add in recirculating loops that automatically purify entanglement without any electronic feedforward, and the technology becomes incredibly robust. So we've mapped this combinatorial universe from front to back and back to front. We've seen how tweaking artificial momentum opens up the entire spectrum, and how turning the physics back on itself creates flawless quantum traps. And it all leads us to this profound realization about engineering at the quantum limit. You don't trap a photon with walls or mirrors or brute force. You trap it with a rule. By merely writing a physical rule that says leaving is a detectable event, the universe complies. So what rule will you write next?